In chapter 13, I'm talking about particle kinematics. From the previous session, we know that the dynamic has two general sections, kinematics and kinetics. In kinematics, we study of the geometry of motion, relates displacement, velocity, acceleration, and time, without reference to the cause of motion. In kinetics, we study of relations existing between the force acting on a body, the mass of the body, and the motion of the body. Kinetics is used to predict the motion caused by given forces or to determine the force and the forces required to produce a given motion. Newton's second law, F(r) equal ma. We start the dynamic with kinematics. What's the application of kinematics? Kinematics relationships are used to help us determine the trajectory of golf ball, the orbital speed of satellite, and the acceleration during acrobatic flying. Generally, we have two types of motion, rectilinear motion and curvilinear motion. In rectilinear motion, position, velocity, and acceleration of particle as it moves along a straight line. But in curvilinear motion, position, velocity, and acceleration of a particle as it moves along a curved line in 2 or 3 dimensions. In this chapter, we are learning about rectilinear motion and curvilinear motion. In rectilinear motion, we are talking about the continuous motion, also about constant acceleration motion, and the last part is erratic motion with motion graphs. But in curvilinear motion, we are covering rectangular components, motion of a projectile, angular motion of line, and also talk about the normal and tangential components and cylindrical components. And the last part is talk about relative motion of two particles using translating frame of reference. In this section, we start with the simplest topic, rectilinear continuous motion of particle. But before that, I'd like to briefly introduce the general definition of position, velocity, and acceleration. If we recall from a static course, the position of particle can be represented by position vector. To do that, we need to first establish a coordinate system. In this case, we consider have a rectangular or Cartesian coordinate system, x, y, and z. The particle now has a coordinate in x, y, and z, and the position of particle is represented by vector r that is drawn from origin to this particle. This position vector r is written by Cartesian form as r equal xi plus yj plus zk. Again, ijk is a unit vector along x, y, and z axis respectively. Suppose that p is in motion relative to the chosen reference frame, so that r is a function of time. We express this by notation r equal rt. Consider after some time the particle moves to new location, p prime, with new coordinates x prime, y prime, and z prime, and a position represented by a new vector r prime. The change in position of this particle, which is r prime minus r, is defined as displacement. As you can see, the displacement is meaning delta r, also a vector. Velocity is defined as a rate of change in the object's position From calculus, we know that it's the time derivative function of position, dr over dt. Also, we can say that the velocity at time t is defined by where the vector r t plus delta t minus rt is the change in position or displacement of p during the interval of time delta t. Therefore, the velocity is the rate of change of position of p, and dimension is distance over time. The acceleration of p relative to the given reference frame at time t is defined by vt plus delta t minus vt over delta t, where vt plus delta t minus vt is the change in the velocity of p during the interval of time delta t. So the acceleration is the rate of change of the velocity of p at time t, or the second derivative of the displacement, or the derivative of velocity with respect to t. The dimension of acceleration is distance over time squared. Note that both velocity and acceleration are vectors and function of time. Look at this example. The position of particle in Cartesian coordinate over time is x equal 5t, y equal 6t in y direction, and z equal 5t in the z direction. What's the vector form of particle position r? From static, we know that r equal 5ti plus 6tj plus 5tk. So the correct answer is A. Now let's look at rectilinear continuous motion. Rectilinear means that the path of motion is a straight line. So again, we want to set up a coordinate system so we can describe the position of particle using position vector. But since it's rectilinear motion, we can simply set up a one-directional axis along the path. Consider a straight line through the origin O of a given reference frame. We assume that the direction of the line relative to the reference frame is fixed. We can specify the position of a point P on such a line relative to O by coordinate S. Measure along the line from O to P. According to the figure, S is a positive when P is to the right of O and negative when P is to the left of O. The displacement of P during an interval of time from T1 to T2 is the change in the position ST2 minus ST1, where ST2 or ST1 denotes the position at time T2 or T1. Once again, ST as a function of time. From T2 to T1, the average velocity is defined by change the position over change the time, delta S over delta T. When the time differences delta T approach to the zero, the average velocity becomes instantaneous velocity, defined as a ds over dt, or the time derivative of the position. Instantaneous velocity may be positive or negative. Magnitude of velocity is referred to as particle speed. Speed is the magnitude of velocity and no sense of direction and always non-negative. When the time differences delta t approach to the zero, the average acceleration becomes instantaneous acceleration, defined as a dv over dt, or the velocity v respect to t, or the second derivative of the position with respect to time. Instantaneous acceleration may be positive or negative. When the acceleration is positive, increasing positive velocity or decreased negative velocity. And when it's negative, we have decreasing positive velocity or increasing negative velocity. In the form of graph, when we have a graph of s versus t, v is equal the slope of the straight line tangent to the graph of s versus t, v equal ds over dt, and the slope of a straight line tangent to the graph of v versus t, the acceleration at time t, a equal ds and dv over dt. Let's look at this example. Okay, if the position of the truck during the interval of time t equal 2 seconds to 4 seconds is given by this equation. What is the velocity and acceleration of the truck during the interval of time? As we know that velocity as derivative of the position with respect to the time, so t power 2 is the velocity and acceleration is derivative of velocity with respect to time, dv over dt equal to t meter per second squared. Now we have learned first two basic kinematic equations. If we combine these two equations and consolidate dt from both sides, then we get the third kinematic equation, ADS equal VDV, that this equation not involve time. These three important kinematic equations, when you solve the kinematic problem, depend on the noun and unknown, we decide which equation we have to use. Let's look at some examples. In this problem, the acceleration is given as a function of position, not as a function of the time, and a is equal square root of s. When we look at the three kinematic equations, we notice that the third equation is meaning ADS equal VDV is true. We substitute A with the position function, integrate from both sides, pay attention to the lower limit of integration, because the lower limit of integration is very important and it's given from problem statement. After integrated, we get this value. Rearrange, we get formula velocity. We find velocity as a function of position. And now we can evaluate velocity when the position at s equals 16 meter. The velocity is 9.24 meter per second. For the second part of equation, we have to find time. We can write the second equation, second time derivative of position. This variable that we are interested. In the previous part, we get velocity as a function of position. From first equation, we can find relation between v v, t, and s. Now we term t to the left side and term v to the right side. Then integrate from both sides. Once again, careful about the initial t and initial condition and position is mean. After integrated, we get this. Now we have a time as a function of position. Normally, we rewrite it position as a function of time because time always independent. Therefore, after rearrange it, we get position as a function of time. This one. And also velocity as a function of time and acceleration as a function of the time. Okay. When the acceleration is known as a function of the time, we can determine the velocity as a function of time by integrated from acceleration respect to the time. If the velocity at time 0 is v0 and at time t the velocity is v, the results show that the change in the velocity from time 0 to time t is equal the area defined by the graph of the acceleration from time 0 to time t. The acceleration can be integrated with respect to the time to determine the velocity as a function of time, and a is an integration constant. Okay. When the velocity is known as a function of time, we can determine the position as a function of time by integrated from velocity respect to time. If the position at time 0 is s0 and at time t the position is s, the results show that the change in the position from time 0 to time t is equal the area under is equal the area defined by the graph of the velocity from time t0 to time t. Okay, let's look at this example. In this example, velocity gives as a function of the time. Initial position is 0 and we need to determine the position and acceleration at time equal 4 seconds. A equal dv over dt. We substitute v as a function of time, perform differentiation and get at. This acceleration as a function of the time. So at time equal 4 seconds, the acceleration is 10 meters per second squared. And for the second part is we need to find the position of particle at time equal 4 seconds. We use this formula v equal ds over dt. We substitute v with the time function and rearrange, and we got this one. We integrate from both sides. Again, pay attention to the lower integration limit. We got this from initial condition that given. After integration and rearrangement, we get the position as a function of time. Now we can evaluate the position at time 4 seconds. The position equal 37.3 meters. Okay. In this example, the airplane acceleration is given as this equation where v is the velocity in meter per second. Determine the time required for the plane's velocity to decrease from 80 meters per second to 10 meters per second. A strategy. The airplane acceleration is known as a function of its velocity. Writing the acceleration a equal dv over dt. We can separate variable and integrate to determine velocity as a function of time. Pay attention to the lower integration limit. According to the problem, at time 0, the velocity is 80 meters per second. Solve for t in terms of the velocity. From this equation, we find the time required for the velocity to decrease 10 meters per second. And the time required is 21.9 seconds. This is end of this section.